So right here, we are looking at how to calculate the type 2 error. And um, let's kind of talk through this conceptually. So we have a null hypothesis that says it's going to end up, our proportion, let's say we're talking about proportions. Our proportion is something. I'll just put P sub naught right here. We don't know what it is. Now, in reality, there could be a true proportion that exists in the population that sits right about here. Now, our significance level says that assuming the null hypothesis is true, there's certain values that we're going to decide make it so that we will reject the null. And that falls in this range right here. Now, and this is known, this is our significance level. This is going to be right here, 0.05. Okay, that comes from the significance level. Now what this does is where the true population is, this is where we're actually drawing our sample from. We don't know it, we don't know where the true population is, but it does exist, and that's where we're drawing our sample from. And anyways, we will, when we draw from this population, there are two possibilities. One is that we draw from this, our sample result ends up over here, and then because it's on the right side of our rejection point, the critical value, we would correctly reject the null hypothesis, and that's the power of our test. All right, but then you could end up on this side, and this would be where we incorrectly fail to reject the null hypothesis. This would be our type 2 error. So I'll just put T2E, type 2 error. So the important thing with all of what I'm talking about is that we don't have enough information to answer this question. And honestly, it's not something we would calculate. So if you ever find a question where I ask you to calculate the type 2 error or the power, and they don't give you one or the other. If they give us power, we can find the type 2 error. If they give us type 2 error, we can find the power. But they don't give us either of those things, and they ask us to find the power or something like that, then you need to look for your escape hatch. And here it says there's not enough information, because we never calculate this stuff in AP Stat. Okay, this requires knowing, among other things, you need to know your effect size. So the difference between those two, your effect size, I'll just put ES right there. You need to know your sample size. It doesn't tell us that. You need to know a lot of factors, and that's just not given in this problem. So that's where we end. Okay, so what we're looking at right here is, this is what we're going to be looking at today, sorry, but honestly, we're only going to do half of this. I was ambitiously hoping we could get through all of chapter 24 today, but that's not a good idea. So we're going to look at significance testing on Thursday. So we're just going to be constructing some confidence intervals for difference of means. Okay, so here's our scenario. Mr. Wilcox's class performed an experiment to investigate whether drinking a caffeinated beverage would increase pulse rates. 20 students in the class volunteered to take part in the experiment. All the students measured their initial pulse rates in beats per minute. Then Mr. Wilcox randomly assigned the students into two groups of 10. Each student in the first drank 12 ounces of cola with caffeine. Each student in the second group drank 12 ounces of caffeine-free cola. All students then measured their pulse rates again. The table displays the change in pulse rate for the students in both groups. Please construct and interpret a 95% confidence interval for the difference in true mean change in pulse rate for students who, like these, who drink caffeine versus who drink no caffeine. Okay, so basically what we have are some sample results, and we had 10 students, and this is the final pulse rate minus the initial pulse rate. So whatever the pulse was, it was 8 more at the end. And it was 2 less at the end whenever someone didn't have caffeine. You can see all the different results. So what we've got are 2 lists, really, of data. And we're going to need to use lists on our calculator. Now, they already give us the mean, but we need more than that. So we're not going to be able to just take data that they throw at us. We're going to have to do some extra work. So the first thing that I want you guys to do is create list 1 and list 2 in your calculator. List 1 can be your caffeine drinkers. And then list 2 can be your no caffeine. Okay, I'll give you guys a little bit of time to do that. Okay, so as you are finishing putting your data in, what we want to do is we want to find the mean and the standard deviation of each group. Now I know that each one of these, I'm going to separate these into two. I've got group 1 and group 2. The sample size of each is 10. So I want to find the x bar sub 1 and the sample standard deviation for 1, and then x bar sub 2, that's the sample mean of 2, and the sample standard deviation for 2. So I'm going to leave these right here, and once you guys have finished putting the data in your list, what I want you to do is run a one variable stats for each list. And then you can plug in the numbers right here. So I will leave that up there and we'll move forward once we got those. There are some maybe different ways that you would round it or express these numbers, but essentially you've got, I'm just gonna summarize, this is about 2.7 right here, and then 2.625 just to show the next decimal over, but 2.62 is also correct. All right, so we need to have all these numbers, but right now we're not going to use them just yet, but make sure that you're calculating these and you have these written down somewhere. Of course, you always want to follow along with this with a piece of paper nearby, just so you can write down all the steps. So the difference in the means, I'm not going to, any one of you can do this. So we have x bar sub 1 right here, and x bar sub 2. I'm just going to get the difference between that because that's our actual statistic that we're testing. All right, we're going to want to have this written down. That's 1.2 when we do the subtraction. Of course, maybe I'd want to actually show a little bit more detail on that, which would be 3.2 minus 2, which is 1.2. Okay, but this is the actual point estimate for our confidence interval. So we took a sample of caffeine, we took a sample of no caffeine, we got the difference between those averages, and now we're going to see if where the true population might be. And so taking care of the point estimate, we need to figure out this margin of error on either side of it. So that's our next step. But before we can do that, we need to talk a little bit about sampling distributions for differences of means. And that's the next page, but make sure you've got these numbers written down. Okay. And I want to try and summarize this in a pretty simple, well, I mean, there's no simple way probably to do this, but remember a sampling distribution would be, imagine that you have a population that you're drawing samples from. And you, in this case, you've got two populations, and you are going to figure out the difference of, you've got this population right here you're going to draw from, you got this population right here you're going to draw from. You're going to get a difference between them, and the difference between them, if here's 0, the difference might be, something, a sampling distribution over here. It's kind of a strange concept when we're talking about differences, but this would be maybe the sampling distribution right here for x bar sub 1, and this would be x bar sub 2, that sampling distribution. Okay, so let's just kind of focus only on the differences. So this one right here. Now, where this ends up, where this mean ends up, is going to be x bar sub 1 minus x bar sub 2. So the actual mean, and this is our mean for x sub 1, this is our mean of x sub 2. I'll put x bar, sorry. These are all the possible samples we could have drawn from the populations. And now we're subtracting them, and we end up with this right here, this mean, which is going to be x bar sub 1 minus x bar sub 2. And the way that we can calculate this is very straightforward. So the actual center, x bar sub 1 minus x bar sub 2, the center of that new distribution is going to be at the mean of x bar sub 1 minus the mean of x bar sub 2. All right. Now, for our purposes, this doesn't, I don't want to say it doesn't matter, but I mean, it does matter. It's important that we understand that. But we're going to be now considering that we create, since this is confidence intervals, we don't have any knowledge of anything about the population. We are using the confidence interval to estimate something about the population. And so we're going to be assuming that our point estimate is where the population is and figuring out a confidence interval to decide if we fall, where it might fall. So now we're going to be looking at x bar sub 1 minus x bar sub 2 as where that falls. Okay, so if this is getting a little bit weird right now, the center is going to fall right here, okay? So we just take our two means and subtract them, and that's where our population would end up. All right, so that's all well and good, and we're going to see that again in a minute. But the shape of this, assuming that our first, I shouldn't have erased it all just yet. So assuming that this distribution is approximately normal and this one is approximately normal, whenever I subtract them, I'm going to end up with a new approximately normal distribution. Okay, so that's what we're going to assume about this. All right, now I'm going to clear it. And now, of course, we have our sampling distribution. I'm just going to focus on this now. This is the sampling distribution of the difference of the means. The difference of the means. So our sampling, sorry, I can think and write at the same time. So our standard deviation right here is going to be given by, okay, we're going to come up with the equation. I'm not speaking very clearly right now. All right, so now let's kind of think through how we're going to get this. We already found a standard deviation when we were looking at proportions. And what we found is that if I wanted to get the standard deviation of proportion 1 minus proportion 2, then that was going to be the square root of the variance of proportion 1 plus the variance of proportion 2. So we added the variances, and that's how we came up with our standard deviation. We're going to do the same thing here, but now we're going to be, of course, switching out proportions with means. So now it's going to be nothing special here, x bar sub 1 plus the standard deviation, the variance of x bar sub 2. And I'm not speaking very clearly. This is standard deviation of the distribution of x bar sub 2. Okay. So now we can work with this idea. I'm going to erase this right here. Okay. And let's first of all remember, what is the standard deviation of means? And this is in your formula sheet. Basically, it's S divided by the square root of N. All right, so if I want to get the variance of this, if I square both sides, in fact, if I square this, I'm going to have to square this as well. So basically, the variance of a sampling distribution of means is going to be S squared over N. Okay, so I'm going to pause right there and make sure everyone is good with this. I know I'm bringing up some formulas that we don't use every day. You might have forgotten them, but hopefully you look at it, you're like, okay, I do remember seeing that before. So we're going to square that to get the variance. But we have variance for two different distributions, our x bar sub 1 and x bar sub 2. And I need to add the variance of each of those. So here's what that becomes. And I'm going to erase my distribution now to create some room over here. All right. So what this becomes is the standard deviation. Actually, technically, it's a standard error. So I might just put S for standard error of x bar sub 1 minus x bar sub 2 is going to be the square root of the sampling standard deviation of 1 squared over the sample size of 1. So this is the variance of our first sampling distribution plus the variance of the second one will just be the same thing, but for 2. And what we have is this square root, because when we add the variances, I want to square root the whole thing to get the standard error. Otherwise, I have the sampling variance. Okay, so this is, I'm about to change pages and we're going to see the same formula again, but I'll pause right there if anyone has any questions. Okay. So here is, again, from these reference posters that I highly encourage you have. You can see the standard deviation that we just came up with. I just wanted to make sure that this wasn't just a random formula that came out of nowhere. So I've got the variance of the first sample and the variance of the second sample, and I'm going to add them together, square root that to get this standard deviation. Now, technically for us, it's going to be a sampling error because we don't know anything about the population, all that fun stuff, but we get the idea. And of course, the middle, the center. So very good. That's really all we need to talk about with this, but we will come back, of course, and use this equation, this formula. So the next thing we want to do is check the conditions for inference. We do have the same 3. We've got, is it random? Is it 10%? Is it normal? So I've got x bar sub 1 and x bar sub 2. I need to check this for. We don't still have the question stem. I cut that off so we have more room, but it does say that there's a random selection. So we can check that both of those are random. Okay, 10%. We are trying to generalize this to a population of all students that might drink caffeine or not. I think 10 students who participated in this is far less than 10%. So we're good with both of those. And the last one is normal. Remember, we have 2 conditions, or 2 ways of checking normality when it comes to means. We can check that our sample size is greater than or equal to 30. Now in this case, we did not meet that. That would be the central limit theorem. So we can't use the central limit theorem to make this work for us. What we can do is look at if the populations, so the population is approximately normal. All right, so if the population is approximately normal, then we're good to go. It doesn't matter the sample size. Now here, I'm not sure that we have enough information. It doesn't tell us that, but here's where we can just use our statistical intuition to decide if people are measuring pulse rates before and pulse rates after and finding the difference between them, it's probably safe to assume that this is gonna distribute normally. Just by random chance, some people will end up with a drop in pulse rate, some will result in an increase, some will be right where it is, and it's safe to say that it's probably gonna be fairly normal. So even though it doesn't explicitly say it, I'm going to assume that this condition is true, and therefore they're both approximately normal. Okay, now if this is an FRQ, I would write something to that effect. I wouldn't just put a check mark by normal, because then a grader might say, how do you know that they're normal? What did you do to confirm that? Okay, but not a whole lot to that since you're already familiar with these tests. Remember, large counts only works for proportions, so don't try and use that as a criterion. All right, this is just to summarize that as well. We can meet one of these conditions. There is the third one that says if we look at if we know nothing about the population, but we look at our sample and it's approximately normal, even though it's less than 30, then maybe we can assume that. In practice, that one just doesn't come up, but it is there. So there you go. Not a whole lot to say about this one. Okay, so now we're actually getting into the calculations. And to start off with, let's name this. We are looking at a 2-sample T interval. So it's a T interval because we're dealing with means. And it's 2-sample because it's 2 samples. That one's pretty obvious. But we're looking And keep in mind that anytime it's two sample, we're always looking at a difference of some kind. Okay, so that's what we call this. And this is where it's gonna get, this is probably gonna be the most confusing part of today. Hopefully everything so far you're feeling like, okay, it's just fallen into place a bit. So now it doesn't get complicated until we get to our critical value, and that's what's gonna be a little bit weird today. But let's start talking about this. We've got the standard equation for this is gonna be our stat plus or minus a critical value times your standard error. And we have that on our formula sheet. So we just kind of, the process would be, okay, they're asking for a confidence interval. I'm going to look to my formula sheet. My generic formula is this. Now I need to figure out, for this particular problem, what is my stat? Well, we already found that. Our stat is x bar sub 1 minus x bar sub 2. And we already even calculated that as 1.2. So I will ignore the number for right now. So if I start plugging in what I know it needs to be, it's going to be x bar sub 1 minus x bar sub 2 plus or minus. The critical value is going to be a t star. And the standard error is going to be s sub 1 squared over n, the variance of the first one, that's n sub 1, plus s sub 2 squared over n sub 2. So the variance of the first plus the variance of the second, and then the square root of that sum. All right. Now we can start plugging in some specific values. I know that my statistic this time is 1.2. There's a 1.2 difference in change of pulse rate. Okay. Plus or minus, I'm going to leave the t star empty for right now. S sub 1, now I did not write this down, but you guys have it written down. Our S sub 1, our standard error for, or the sample standard deviation for the first one was 2.7 essentially. You can be more specific if you wanted to get down to like the 2.699, blah, 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 whatever. The sample size was 10. And then for the second one, it was 2.625, also over 10. So I hope that you guys are good with this. So far, we are just plugging in numbers, plugging in the correct equations to begin with, then plugging in the correct numbers in the right spot. Then we get to t star, okay? And this is where it gets a little bit, more than a little bit, quite confusing. Okay, now here is the shortcut you can always do. We had 10 in each sample. If we were looking for a normal degrees of freedom, we just take a sample size and subtract 1. Okay, but which sample size? I don't know. So the shortcut, if you want to do this the easy way, and you just need to write a sentence saying, I will be conservative with this one. We're going to see the way to get a very exact confidence interval also. But let's say, I'm going to change this. Let's say it was 18 in this group and it was 10 here. We always get our most conservative interval by looking at, by having the smallest degrees of freedom. If you remember, when you work on the table B, no matter what confidence level you're looking at, if it's 90% or the 99% confidence level, no matter which one it is, you got all these numbers right here, the numbers get bigger as you go up the chart. The fewer degrees of freedom you have, the bigger your critical value is. Okay, and think about what that means. If I'm putting in a t star right here, and that number keeps getting bigger and bigger, the fewer degrees of freedom I have, then I'm going to get a wider and wider interval the fewer degrees of freedom I have. So your most conservative estimate is to take a small degrees of freedom. So right here, pretending that we had 18 and 10 in our two samples, then I would just get the degrees of freedom of this one, and my degrees of freedom here would be 9, and I could just use that. It's a very simple calculation. It results in a conservative confidence interval, and as long as you write something to that effect, explaining why you chose that degree of freedom, then you're good to go. Because keep in mind, there are people who take this AP test who do not have access to calculators. And you can take the entire AP test without calculators. So that would be a sufficient way of doing it. What I'm about to show you uses your calculator. All right, so let's say we want to get more precise. We want to get the narrowest confidence interval we possibly can. I'm going to go back to now my original numbers. I'm going to get rid of this. Okay, so what we actually have to do is we're going to need to run this entire test on our calculator. And if you guys have been reading the chapters, you've probably seen as we've gone through our inference tests that there are lots of different ways of doing these tests automated on the calculator. And I've intentionally not been showing you how to do that because you need to be able to show all your work by hand. So some of you will just be looking at this for the first time. You're going to get pretty upset with me. You're like, you've been making us do so much work and the calculator does it all for us. But I don't want you to have the calculator do it for you. But here's what I want you to do. On your calculator, you already have these lists put in. So go to Stat, and then once you're in Stat, go all the way to the right where you see Tests. And look right there, you've got a 2-sample z-test, a 2-sample t-test, a 1-proportion z-test. You've got a z-interval, a 1-proportion z-interval, all kinds of things available to you. We're gonna go down to 0. You can just hit 0 if you want. And that's a 2-sample t-interval. And once you're there, so again, that's 2-sample t-interval, which is option 0. You have 2 input options. One of them is data and one is stats. We're going to input data. And we've got our data already put in list 1 and list 2. Don't change the frequency. The confidence level is 95. Do not pool the data. So hopefully I'm not going too fast. Hopefully you're following along with your calculator. You can see all the list 1, list 2, frequency 1, 2, confidence level. All right, once you've got that put in and you know you got it right, you can calculate. And this is gonna give us our final answer. In fact, I can write this down right here. This is gonna be negative 1.302 to 3.702. We're gonna confirm we get that number here in a minute. The calculator did it all for me automatically. It's a good thing to know this to double check your work, but do not just answer this question by plugging numbers in and showing what the confidence interval is. Okay, that is not gonna work. All right, so what we are doing this for is because if you look at your answer output, it gives us degrees of freedom. In fact, my degrees of freedom right here is 17.986. And it goes on, of course. So you can see that we end up with a decimal number. Now that's because the actual formula to calculate this is very complex compared to some of the stuff we do, and it's not worth our time to calculate it. We're letting the calculator itself do that for us. But we end up with this formula, you can end up with a decimal degrees of freedom. And I want to point out what this is close to. If my degrees of freedom for N1 is 9, and my degrees of freedom for N2 is 9, and I add that together, I get a combined degrees of freedom of 18. This is really close to that, but it's not quite, and we don't want to assume that it's just double. I mean, that's a terrible assumption. You always go more conservative by reducing your degrees of freedom. Okay, but this is the exact degrees of freedom for this problem. Okay, now this is not something we can plug into our critical value. What we need to do is we want to figure out where that would be. Oh, sorry, and I just deleted stuff a bit early. No, I don't want to do it that way. Okay, so if I think back to table B, you know, I've got all these numbers. Somewhere there's going to be 17 and 18 degrees of freedom. And then we're going to have the 95% confidence level. So we've got a couple of numbers right here, and our number is going to be pretty close to 18, but not quite. But we can get an even more exact t star by using inverse t on the calculator. So now that we know our degrees of freedom, I'm going to go now to inverse t, that's distributions, and it's the fourth option. Okay, and this is where we've already gone over stuff like this. Okay, but if I am picking a 95% confidence level, I want to find the 95% that's the middle of the data. So this right here is my 95% of the data. I don't want to have 2.5% up top. That's where I don't care about, and 2.5% at the bottom. Okay, so if that is my, what I'm looking at right now. Okay, things are going slow. I don't know if my internet's getting choppy for you. Okay, that means that I want to have an area under the curve of 0.025 right here, 2.5%. So for my area, I'm going to put in 0.025, or I could also put in 0.975 because that represents the middle 95% of the data, and I'm showing where is the cutoff so I don't get the upper 2.5% and the lower 2.5%. So I'm going to put in 0.025. Again, you can find this at the bottom of table B, or sorry, at the top of table B where it says tail probability. You can just see for 95%, it's going to give you 0.025. Okay, so 0.025 is the area. The degrees of freedom is 17.986, which gives me a critical value finally of, you can ignore the negative, it's 2.101. So we're going to do another example in a minute. We're going to go through this process again, but basically we need to run the t interval test on our calculator to get the degrees of freedom. And then we need to use inverse t to figure out what our critical value is. So it's a two-step process to get the most exact t star that we can. But now that we've got it, I'm going to plug that number in, 2.101, and now I can do some calculations. I'm going to create some room for myself right here to finish this out. All right, there's my margin of error. I'm going to add and subtract that from my point estimate. And sure enough, if I compare this to my calculator printout from earlier, it's exactly the same. All right, I'm going to pause here to see if there are any questions. So now that we've got our confidence interval, here's the kind of quick summary of that. Here's our confidence interval formula. And I'm not going to keep it up there. We'll show that again, or I'll write it up again later. Now we want to interpret these results. Do we have convincing evidence that there is a difference in the pulse rates of people who drink caffeine versus those that don't? And this goes from negative 1.302 to positive 3.702 is our confidence interval. And this is where we need to remember, if we have a confidence interval that includes 0 and straddles positive and negative numbers, then we don't have convincing evidence that there's a difference between them. Okay, so let's kind of answer this. Do we have convincing evidence that there's a difference? I will say, because the confidence interval contains 0, we do not have convincing evidence that there's a difference and here's where I'm just going to copy this from the question, that there is a difference in the pulse rates of people who drink caffeine versus those that don't. Okay. And we could also include our confidence interval. You know, we could shove that in right here just to show with numbers. So we want to remember what the confidence interval is saying. The difference between our two populations that we took samples from could range anywhere from negative 1.302 to 3.702. So there could be a difference, that is, but we cannot be sure. So that's, I mean, I guess that's where we're stuck at it right now. But if it's a positive number, that means that our first mean is greater than our second mean, because we're always doing x bar sub 1 minus x bar sub 2. So if we end up with a positive number, that means that x bar sub 1 is bigger. But for those negative numbers, that's where our x bar sub 2 is actually bigger than x bar sub 1. So because we can't definitively say that one is bigger than the other, we're just no convincing evidence. That's all we say. All right, I think that's enough said about that, unless there are any questions. Okay, and here you've already seen this, but this is an interpretation of it. If both bounds of your confidence interval are positive, then P1's greater, well, not P1, x bar sub 1, or sorry, mu is going to be greater, mu1 is going to be greater than mu2. If they're both negative, then the other way around. But in our case, when we have a negative and a positive, there's no convincing evidence, just to summarize that. So this is a good one. I'm going to pause real quick and let you read through this problem. Okay, so as you're finishing reading, this is actually refers back to a previous question where they looked at 3 different things: the average number of, the number of brands remembered while watching specific types of show, and they had it broken down into violent shows, neutral shows, and then shows with sexual content. So right here in the prompt, it already says we're just going to rule out sexual content. So basically, now the executives are deciding, should we run our ads during a show that's violent or a neutral show? And we're not doing any calculations on this. They just give us the confidence interval that shows us the difference between violent shows minus the average number of brands remembered watching violent show versus the average number of brands memorized or remembered after watching a neutral show. And looking at this, what would you say? Does it seem like we have any conclusive evidence that one is preferred?
Is it neutral shows?
All right, neutral shows seem to be better if you want someone to remember your brand. Because yeah, remember, because we end up with a negative here, and it's printed out a little weird, but that's a negative number as well. Because we have two negatives, that means that the average remembered during a neutral show must be greater than the average remembered during a violent show. Because the only way we get negative numbers is if this term is bigger. So this is telling us that more brands are remembered during neutral shows, so it's in their best interest to pursue neutral shows. Okay. So it's just an interpretation question here. And I don't know what more to say, but you can kind of look through question 23. I don't remember if 23 is in your homework, but yeah. You can look through that and look at the answer at the back to kind of get some more information on something like that. Now, we are skipping this. We're going to do this on Thursday because it's not a good idea to try and teach all that today. And we're just going to wrap this up with a confidence interval problem. So you can get one more example. We'll go through it somewhat quickly, I guess. And we'll kind of answer this in this way. So they give us A, B, C, and D. So I'm just going to ask you guys, what do the box plots suggest about differences between male and female pulse rates? So sorry, before you answer, we're looking at pulse rates again. You can see a bunch of data. So you can take a minute to kind of look through this and familiarize yourself with it, and then we'll answer those questions. All right, so what do the box plots suggest about differences between male and female pulse rates?
The means are about the same.
Okay, means do look pretty much the same. In fact, we can see the numbers up above, but just the box plots themselves kind of show that. Anything else?
Females have a wider range of pulse rates.
Wider range, there we go. So just initially, I would ask, do you think that there is a difference between the average pulse rate of a man and the average pulse rate of a woman?
I would say no.
Okay. I think that's a fair starting point. Of course, we can calculate and find out for sure. Remember, if we get two negatives or two positives in our confidence interval, that's going to show us, yes, there is a difference, or there's likely a difference. But if it's a negative and a positive in our confidence interval, we can say there's no evidence. So, I mean, as close as those two are, it doesn't look like there's a real difference. Okay. Is it appropriate to analyze these data using the methods of inference discussed in this chapter? Explain.
Yes, because it meets pretty much all the conditions.
Okay. So that's good. I'm glad that you're putting it into those terms. So the conditions, is it random?
Yes.
Yeah, I think it's safe to say. It doesn't explicitly tell us that, but it's pretty safe assumption if it comes from research. Okay. 10%?
Yep.
Definitely. Yeah, we're talking about men and women, and we're looking at not very many. Okay, now normal.
Both of the box plots look pretty normal.
Excellent, excellent. Because what the first thing you can rule out is that we did not meet central limit theorem. We got 24 and 28, so neither of those are 30 or more. So we have to look at the population distribution, and that is exactly, or really we're looking at our sample distribution right here. Both those sample distributions appear to be normal. So you got to be able to interpret from a box plot and decide that. So yes, very good answer. Excellent observation. So, okay, we're good on that. We've kind of jumped through that planning stage. We know what our, we have checked our inferences, our conditions for inference. Man, I can't talk. So now we're going to jump to the heart of the problem, which is part C. We're going to create a 90% confidence interval. So I want to, first of all, just state this is going to be a 2-sample T interval. All right, next thing I want to do is come up with my basic formula. That the generic formula for this is going to be your stat plus or minus the critical value times the standard error. And more specifically for this problem, it's going to be x bar sub 1 minus x bar second. X bar sub 2 as the stat plus or minus the critical value is T star. And our standard error is going to be S sub 1 squared over N sub 1. So it's the variance of our first sample plus the variance of our second, which looks like this. And these numbers are all found over here. This is going to be 1. That's going to be 2. So we can plug that in. The mean difference, I'm just going to subtract right here, 1 minus 2. So that's going to give me that right there. I'm rounding off when I write this in my equation, but I'll probably plug the full number in when I do the calculation. Okay. I'll pause right there to make sure that everyone's good with those numbers so far. Okay. And my question is, if we didn't want to bother with technology and we just wanted to pick the most conservative value that makes sense, what degrees of freedom would we use?
Uh, 23.
There you go. So if, you know, it's always legitimate to do this, but we would pick the smallest sample size and get the degrees of freedom of that. So our smallest is 24. 24 minus 1 gives us degrees of freedom of 23. That would give us a wider confidence interval. What we're going to end up with using technology is a confidence interval, you know, we'll pretend it's that big. By using more degrees of freedom, it might be, you know, that big. You see how it's just a little bit wider? So what using technology does is it gives us a more precise, narrow confidence interval. So overall better results, but it's not that big of a difference. Okay. So I'm going to just get rid of these for now. And we will use technology. So what we're going to do is we're going to have to plug this into our calculator. So again, it's stat over to tests, and then it's 0 for the 2-sample T interval. but now we're not using data. We can't use the lists. They didn't give us the actual data points. So I'm going to use the stats, and I'm going to plug this in. I've got my X bar sub 1, my sample standard deviation for 1, and my sample size for 1. I'm going to have to plug those in from that data table given. So once we run that, of course, the only thing we're really going to be looking at is the degrees of freedom that we get as a result. Now you can see the actual final confidence intervals. So we're going to double check this against our calculator later. We should get negative 3.025 and positive 3.2753. Remember, the reason we don't just plug this in and do it is because AP readers are looking for a very clear logic, a very clear line of reasoning that led you to your answer. And simply showing up with your answer without giving all these details is not sufficient. Okay, so hopefully everyone got the 40.231. And now I want to figure out my critical value. So I'm going to go to distribution, second, and variables. Number 4 is inverse T. Because this is a 90% confidence level that we're going with, I can look up on table B up at the very top. For a 90% confidence level, my tail area is 0.05. So I'm going to put that in as my area. And my degrees of freedom, 40.231. And I got a T star of 1.684. I'm not worried about the negative. Okay, and once I've got that, I just plugged it in for T star in my calculation, and then I can go from there. So any questions on this? Okay, take a minute to calculate this, come up with your confidence interval. Okay, and for those of you who are still wrapping up, you can run through your calculations. I've got them put right there, and I can compare those to what the calculator gave. Because they had a little bit better precision, theirs is 1/1000th off of what we got. In other words, we got the same thing. So the only thing left to do is to kind of wrap this up. And now they ask, does this confidence interval confirm your answer to part A? But what we can say is we want to wrap this up using our template. It says, because the confidence interval contains 0, we do not have convincing evidence that that there's a difference, and I'm just going to put ... right here. We don't have convincing evidence that there's a difference in pulse rates between men and women. All right, that's the problem. You've done it. So hopefully that doesn't come across in the end as too awful of a calculation process. I know finding that T star is no fun. It's not as straightforward, but keep in mind, we don't just have one sample we're drawing from. So like, oh, let me just subtract 1 away from the sample size and get my degrees of freedom. We have 2 samples. So it gets a little bit more complex. And you can see kind of the reason we're not even doing the formula, we're letting the calculator do the work for us. All right, so I'm going to clear that. And we're going to call that good for today. I didn't want to try and squeeze in significance tests. So we're going to do that first part of class tomorrow and hopefully still be able to do part of chapter 25. So read chapter 25. One thing I want to mention about chapter 24, those of you who read it, it does have the very last section of that chapter talks about pooling data for means. And that requires some pretty big assumptions. And I'll just tell you, in AP Stats, we never pool for means. But hopefully some of you guys take some more advanced stats when you get to college, and maybe you'll get to some scenarios where you do all kinds of stuff that we're kind of glossing over. So anyways, anything you read in chapter 24 about pooling, ignore that. We only pool for proportions. Okay, I'll say that again. You only pool for proportions. Okay, I've done enough talking for today. Read chapter 25. Here's your homework. Anything that deals with significance tests, you can skip. I intended to get through that and we didn't. So yeah, that's about it. If you are good to go, you can have a wonderful day. But if you have any questions, you can stick around and we'll talk about it.